One of the best examples of complex numbers is that we can factor polynomials. Now, as an example of that, we'd like to look at a undriven RLC circuit. So let's consider a resistor, an inductor, and a capacitor. And let's imagine that our circuit is then connected so that at some point we have a current and a charge on the capacitor. Now, we would have to have some initial conditions to set this up, but we've talked about that when we have an RLC circuit. So if we circulate around here, we have our differential equation. So in this case, there will be minus signs with every term. Minus L di dt, minus Q over C, minus IR is 0. And here we have the condition that I is equal to dq dt. So I can write a differential equation immediately in terms of dq dt. I'd have L, I'll multiply the minus sign through, plus I'm going to move this term over here, dq dt r, plus Q over C is 0. Another approach that you could do is differentiate this equation, and you would get a similar differential equation for current. So this term would be di dt r, and over here, this would just be I over C. So in both cases, we have a second-order linear differential equation with a damping term that's in here, this term di dt r. And now what we'd like to do is show the power of complex numbers to solve this equation, actually complex functions. So we'll look at it like this. We'll conjecture a solution where we have that let's focus on this equation first for current. We could do it with charge or current. So let's write our current as an amplitude A times a complex number Z. So Z here is some complex number. Now, here, if we take two derivatives of this, well, let's just take first one derivative of this function. And that's very simply ZA e to the ZT. And a second derivative of this function is equal to Z squared A e to the ZT. So if we substitute the functions, the first and the second derivatives in here, we just get L Z squared. Now, I'm going to save the A e to the ZT, because it's in every single term, and put it out on the outside. This second term is Z times R. This last term is 1 over C times A e to the ZT equals 0. Now, what we have here is a complex polynomial, and a solution to this equation is when this term is 0. And I'm going to write that characteristic polynomial, it's called the characteristic polynomial, by dividing by L. And so I get Z squared plus Z times R over L plus 1 over LC is equal to 0. We'll solve this equation for the complex quantity Z. Now, this is the beauty of complex numbers. Any complex polynomial can be factored, and we can use the quadratic formula for this simple case, where we get that Z is equal to negative R over L plus or minus R over L quantity squared minus 4 over LC to the 1/2 divided by 2. And there we are. Now, let's look at what happens first. There's 3 possible cases. So we have the simplest case, I, is when R over L squared equals 4 over LC. And then we only have one real solution to this equation, because this term is 0. And Z in that case, is real. The second case is when this quantity inside is less than 0. And that's how we're going to see an imaginary quantity coming out. So let's first define 4 over LC minus R over L quantity squared. Let's call this quantity beta. And let's make this bigger than 0. Then what we have is minus beta on the inside. And if you remember that the square root of minus 1 is I, then we have solution Z is a real part plus or minus I times, and let's make beta equal to this to the 1/2, and we have I beta all over 2. Now, this solution is the one that we're going to be interested in. It's called lightly damped. This one here, where this quantity vanishes, is called critically damped. And our last case is when case 3, when the quantity inside that square root is positive, then this is a real number. And so we have 2 real solutions. So this is called overdamped. And so we were able to characterize the solutions to this circuit by using complex numbers, finding the characteristic polynomial, solving it, and looking at 3 special cases. The case that we've been often considering is the lightly damped case, and we'll talk about that one in a moment. We'd like to explore the lightly damped solution in a little bit more detail for the differential equation that described this circuit, where we took our circuit equation and differentiated it, and we're trying to solve for the current in this equation. Now, our current in the lightly damped case is equal to an amplitude times an exponential of a real factor, r over 2L times t. This is a decaying exponential times, there's 2 possible solutions, plus and minus, times a sinusoidal varying piece where the oscillating frequency beta is given by, now let's write beta over 2, because if we put in beta over 2, we get 1 over LC minus R over 4 R over L squared to the 1/2. And what we see here is in the oscillating frequency that we have the underlying frequency of the pure LC circuit, but it's a little bit, the oscillating frequency is a little bit less by this second term. So the oscillations here are damping down by an exponential. And one way to write that is to put a little exponential envelope. And then depending on where we start, our oscillations are damping down. So we're looking at the current as a function of time. The oscillatory frequency is not the underlying frequency of the LC circuit, but a little bit different. And this exponential factor is damping down. That's why we call it a lightly damped solution to this problem. And you've already looked at this case in terms of energy when you were analyzing the undamped RLC undriven, when you were looking at the damped RLC undriven circuit.